So the title of the talk is rather long, a methodology for deblurring and recovering conformational states of biomolecular complexes from single particle electron microscopy. I will explain some of the terms here. The term single particle usually refers to anything that is not crystallography, because in crystallography you have a basically network of molecules aligned together, but here there is only a single molecule. There is no arrangement. And cryo-EM is a specific class of single particle imaging, which my talk will be about. And I will explain briefly what this cryo-EM is exactly. So here the idea is that you want to get a three-dimensional density map of your molecule, basically. The structure of the molecule, three-dimensional structure from two-dimensional projection. So you can think about like tomography, basically, but there is a big difference between a standard tomography here that the angles of projections are not known, and this is part of the problem. So this gives you resolution usually, which is much less than crystallography, but it's preferable in some applications to crystallography because crystallization is a lengthy process, and also in some cases you do not want to your biomolecules be crystallized because they will lose their actual shape, and function will not be recovered from that shape. So for that reason, cryo-EM is becoming one of the most popular way of getting three-dimensional structure in structural biology. Now the challenge is that for several reasons, this is a very, you have an extremely highly strong noise, and which makes it the problem very difficult. You can have noises, signal-to-noise ratio of 1/100, so the signal can be basically 1/100th of the noise. So noise will be extremely strong. And the 3D volume reconstruction becomes an extremely difficult and complicated problem. So I want to be very humble here. What I'm not proposing is not a really grand solution to complications in this problem, and we haven't tested it in real-world data because that requires lots of other biological and practical requirements. So this is just a simple, you could say, toy model for this problem. Okay, so the basics of cryo-EM is that you have a very thin layer that you put your sample in it, and then basically you have your, here little bit the picture might be misleading, but in ideal case you have the same molecule being distributed randomly at different orientations and positions within that thin film here. So these will be in ideal situation, all of them will be the same molecule at random locations and positions. And here where our SE3 methodology comes to the picture. But then you will get, what happens is that then you will have a projection. You will get millions of these very tiny two-dimensional projections all over the plane. So and if there is no noise, then you can recognize the similar ones, saying that they all come from the same direction, basically. And then you have now a bunch of projections. The problem will be to recover the three-dimensional structure from many different projections, and still it's different from a standard tomography because you don't know the angles. You have to find the angles first. And there is a method called the method of common lines, which lets you to find the angles. But in practice, the signal-to-noise ratio is so high that you cannot look at them and decide which one is similar to other ones. So there are lots of classification and clustering algorithms being done to classify projections coming from the same direction, doing certain form of averaging, alignment and averaging to reduce the noise. At the end, then, you will have some blurred images, 2D images, which are the projections. And then you do a method of common lines to get the angles, and then you do back projection method as a standard tomography to build up the 3D molecule. So this has been done and still is a complicated process. It's not perfect, but now in our setting, we assume that we have such an algorithm that's giving us the 3D reconstruction. But what happens in practice is that for at least for two reasons, what you will get will be very blurry. The first reason is that, obviously, because of noise, you will have different angles different projection angles, projections coming from different angles being blurred and mixed together. And this results in inaccuracies all over the reconstruction, and you will get blurring effects. The other one, which is also important, is about your molecule being at different conformational states. So here is an example. This is for certain biological complexes. This is very common. So you can think about your complex as being comprised of two very large subunits. For example, here's like a hinge one. So you have this is one ellipsoid, this is another ellipsoid, and they make an angle. But throughout the sample, you could have molecules being not exactly the same angle, being at rather different angles. That could reflect their different functions in terms of biology, or it could come from just small perturbations. And this would result in, again, errors. Okay, so this is one example here. The angle between the two subunits is 30 degrees between the principal axes of the subunits. Here is 45, and then projections along the same direction will give you something different. By the way, here the SNR is 1/10. In reality, you can have SNR of 1/100. So basically, you couldn't see anything. So now, in the next step, we try to model these two types of blurring through convolution by SE3 kernels. So obviously, we don't know the kernel, but this is just a formal way of describing it. We assume that you have a density map, the 3D volume rho, and then you have an unknown probability density on SE3, which causes this deblurring, this blurring. And the way we go about it is that we look at the standard action of SE3 on R3, which is through rotation R plus translation. And then basically you can do think about it as kind of averaging, weighted averaging, and the same way that we do convolution of adding to standard Euclidean random variables. Here is the convolution, SE3 type convolution, which gives you the the probability density of the body when a kernel perturbs it. Okay, so this is just a formalization. The next step is that we try to parameterize this kernel F so that we can go to basically an inverse problem setting to find it or estimate it. So obviously the deconvolution and deblurring scenario is very complicated and ill-posed. But in certain applications, it happens that you have a large biomolecular complex, and through other methods, you know the shapes of each subunits. So basically, you know the subunits. The only thing that you know is their relative positions. Okay, so we work on that regime. This is, I mean, our biologist colleagues say that this has applications, and we believe them. So we think about a complex which is modeled as n subunits. And then the blurring effect will be something like this, the summation of convolutions, basically. But there will be two components. One, the Fi will be acting on the body I. This will be the motional blurring, and this K common to them, to all will be the effect of reconstruction. So, but for this purpose of the rest of the talk, I will consider K convolution Fi does the same. So this convolution is the SE3 convolution between two probability densities on SE3, but this was a different convolution, which was the group action convolution, just to be clear here. So now, just a remark, the setting that we are thinking about is the body are deterministic, but we model them as ellipsoids. And then we think about an ellipsoid as basically modeled by a Gaussian with given covariance to make the problem easier for presentation, basically. But you can think about it perhaps other ways. So the setting is that we have a random variable R, which has a covariance CR and the mean 0, and then there is a group kernel acting on that variable, basically. So, and this is the starting point, and then what we do is that we try to parameterize the probability density, the kernel that we have on SE3 through its mean and covariance. So this is the algebraic or bi-invariant mean, which you define as a point where the logarithm of the expectation of the logarithm as a point mu g, where the expectation of the logarithm of g, mu g inverse times g becomes 0. So this is a kind of a standard way of defining mean for on SE3, for example. This is a barycentric definition, basically. And then you can define a covariance on the tangent space for that. So if you think about this, for the mean, you will have 6 variables. For the covariance, you have, I think, 21 variables. The total, you will have 27 variables. So you can parameterize this Gaussian type kernel on SE3 with 27 parameters. It turns out that this is too many parameters. We cannot recover it back, because the next step that we do is that we try to do moment matching between observation and what we have. So the observation is this y. The R, the distribution of R, we know that, we assume that we know it. So we know its covariance and mean, assume it's 0. So we try to relate the first order and second order of moments of y to first order and second moments of R through the unknown moments of G or R and T, the SE3 variables. Now, if you do this, you will get something like this that relates the expectation of y to expectation of, and to mu g, for example, the mu t here is the translation component of mu g. This omega r is, the expectation of omega r is related to the covariance that I talked about, the SE3 covariance. And the same thing, the covariance of y, you can write it in terms of the covariance of G and the covariance of R. Okay, so basically you have, those who have worked in, for example, blind source separation are familiar with this matching of moments from the observation to the known variables, basically. So the next step is that we will have a, okay, so another point here is that, again, because of if you do this counting of variables, you will see that the number of observations, this side is you observe these variables, still this is an underdetermined problem. So we have an ill-conditioned inverse problem. So we then cheat a little bit, and then we say that, okay, let us assume that our covariance is a very simple structure. Basically, we assume a diagonal covariance at the tangent space, and we assume that the rotation and translation at the tangent space, or Lie algebra level, are independent. So we only have 2 covariance variables. One is the single number, sigma r squared for rotation, and sigma t squared for the translation. In this case, you will have a smaller, simpler simpler formula. Basically, the expectation of y will be 1 minus, up to second order, will be equal to 1 minus sigma r squared times mu t, which is the average of the translation part, and a similar, more complicated formula for the covariance of y related to the covariance, the rotational part of the covariance and the translational part. So in this case, we have 9 equations and 8 variables. So there is some hope for being able to recover the unknowns, which are the mu r, sigma r squared, mu t, and sigma t. And you see that these are still nonlinear equations. They are multiplicative here. And just to give an idea how this, what we call the isotropic Deblurring kernel looks like, this is what you can achieve by Deblurring basically a unit vector with sigma r and sigma t SE3 Deblurring that I mentioned here. So the original thing is at the middle, a unit vector, and this banana shape is after you try to blur it. Okay, so when we did, basically this is the, or should I go back again? I just want to solve this coupled equations by observing this side to find the unknown variables, okay? And I do it by fixing everything and trying to minimize the others, okay? So, and for the mu t part is easy because I assume that sigma r is known and I find mu t. And then for this part, for the second equation, I try to minimize the Frobenius norm of the left and right, okay? And then this problem also tends to be a little bit ill-conditioned, so I add some regularization terms, and then here try to do some, again, alternating minimization. Look that here you have basically an eigenvalue decomposition. At the part of this problem for mu r will be eigenvalue decomposition. And that also gives some sort of indeterminacies in terms of how to select them, and then we just do some minimization to find that the best selection here. So this is an example. This is the original conformation. Then we apply 2 different Deblurring kernels, and you see that the result of Deblurring is that the volume has bloated and becomes fatter, basically. And then we try to fit this covariance to these so basically a permutation of them and find the best matching to see which one corresponds to what. And it turns out that the error for mu i will be mu I and ti. The means will be pretty small, but the error for covariance becomes large. And that's something a little bit puzzling. We haven't found out why, but that's what we observe. So to conclude, I just explained a simple way to think about Deblurring images, 3D volumes in cryo-EM. This is a very early steps, and we reached at certain nonlinear equations for inversion or which were ill-conditioned. And the next step would be try to find better regularizations to solve this problem, and also think about using other modalities, for example, SAX or small angle X-ray scattering data can also, from the same molecule, can be used to do this solve this inverse problem in a better or more informed way. Thank you very much. That was the end of.
Very much. We have time for questions.
Yeah, I have a few questions. First, in the experimental setting, there is only one direction of the rays?
Yes, so they put it in a thin film, and then there is one direction for projection, but the molecules are randomly oriented, so that's why you get different projections. Yes.
Is there any possibility to change the direction to have multiple?
There are ways of doing that, but that's called something different, and I think in the early days they did that, but for some practical reason, I think it's not popular anymore. I'm not expert in that, I don't know, but that's the thing.
Probably this is due to the fact that when the electrons hurt the molecules, or they are burned No.
Yes, so
we cannot do anymore.
one of the reasons that the signal-to-noise ratio is so bad here is that because the electron beam is really weak, so that not to burn the sample.
My second question was, you added some regularization. How did you choose this regularization term?
Just by experiments,
By
yeah.
experiments. Okay. And finally, I didn't see when you mentioned that there are the number of the parameters to estimate, the number of the, I didn't see how you arrived at 9.
So the a mean matrix for in SE3 has 6 parameters because you have 3 rotations, 3 parameters for rotation and 3 parameters for translation. And then when you go to the covariance matrix, then you have 6 parameters time. Basically, you have a 6 by 6 matrix.
Okay.
So that becomes, I don't know, 21 variables.
And then by symmetry.
Yeah, yeah.
Okay. And yeah, finally, I had one more. You mentioned that here you limited yourselves to the first 2 moments, mean and covariance. Do you think that trying to have higher order moments?
We haven't
like
tried
in
it, but
Blanchard?
definitely that's one possibility, yes. Again, but in practice, so I just want to be very modest about this. In practice, many other things can show up, which derail everything, yes.
You mentioned the relation of with blind source separation.
Yes, so that's
blind
what,
source separation.
yeah.
One of the techniques is using higher order.
Yes,
moments.
definitely, yeah, yeah.
Okay, we have time for one more question.
Question is with regard to the modeling of noise in on the group SE3. So you used this banana distribution, but it seems to me maybe using a diffusion model would lead you to nicer analytic formulas for the moments you are trying to fit.
I didn't get your question. Is that you're talking about this equation, for example, here?
Yeah, the distribution of G, basically, which you introduced.
So yeah, the distribution of G, okay.
You introduced a distribution where the logarithm of G is, the group logarithm of G is normally distributed, yes?
Yes, yeah, yeah.
And I believe the problem would be easier to solve if the distribution of G came from a diffusion model, kind of Brownian motion on the group. However, the 2 models agree to first order, so it would be interesting actually as a way of maybe regularizing your mismatch between number of variables and number of equations.
Okay.
Yeah.
That's very interesting. Yeah,
Yeah, I believe Shirikshian would be very familiar with that actually.
Yeah, that's, but that will become more complicated, no?
No, I believe it would become more simple analytically, but that remains to, actually, maybe we can talk about it.
Sure, yeah, yeah.
Yeah.
Okay, thank you very much.